Good afternoon. Hi, I'm Jan Hong, lecturer and consultant from the practice of artificial intelligence in Institute of System Science. Today, the topic I'm going to talk about is learning with small data, few-shot learning. The term small data is the opposite to big data. So far, there is no widely accepted definition on small data, and the use of it is still pretty ambiguous. In any case, for today's talk, small data refers to a data set that has so few examples, and the usual deep learning cannot learn anything from that. For this kind of situation, a different kind of strategy, a different kind of approach is needed to train our AI model, and we are going to discuss the strategy that can achieve that. It is called few-shot learning. We are going to take a look. Why do we need few-shot learning? What is few-shot learning? What are the approaches available so far that can train AI on data set with very few examples? Now, unfortunately, few-shot learning is a technical topic. In this talk, I will try my best to simplify the ideas and concepts involved in this field using simple examples and illustration to make things easy to understand and digest. However, there are times when explanation through mathematical equations is still easier and better, and thus you encounter a few mathematical formulas in this talk. But no worry, you will be well guided, and in-depth understanding on those formulas is not required. Here is a broad overview of AI. It started early in the 1950s. As you can see in the image, this AI can play chess. Not very useful, but amazing. To get AI to play chess is not that particularly tough. We just need to set rules. Since the 1980s, we have a new thing called machine learning, and it started to flourish. One of the important applications that uses machine learning is filtering spam email. So the AI will identify which email is a spam, which is not a spam. It has become part of our daily life. So instead of using rules, in machine learning, we tell the AI what to extract from email, and then use statistical algorithm to decide if we should classify this mail as spam. In machine learning, we humans do not set the rules. Instead, we tell computer what information to get from the input and let the computer to figure out what should be the correct outcome or decision. This is where the learning happens. Since 2010, as you can see in the figure, the deep learning has become the main engine for AI. It is now widely used to analyze image, video, sound, and do many other things not feasible in the past. Basically, deep learning also first tries to extract certain information from image, video, or sound, and then use some statistical related algorithm to do classification, identification, or make decision. But there is a big difference between machine learning and deep learning. In machine learning, we tell the AI what to extract from input. In deep learning, the AI learns by itself what to extract from input. And for this kind of learning to happen, we need to provide a lot of data. Besides that, we also need computers that can do a lot of computation in a relatively short time. Here, we have a chart produced by OpenAI. This chart shows the amount of computation required for training each state-of-the-art AI model. On the x-axis, we have the year when those models were released. On the y-axis, we have values running from 1 to the power of minus 14 to 1 to the power of 4. and the unit is called petaflop per second day. And here, 1 petaflop per second day basically denotes 10 to the power of 15 neural net operations per second for 1 day, or a total of about 10 to the power of 20 operations performed in a single day. And that is a lot. If a model needs a petaflop per second day to complete its training or learning, it means the model requires 10 to the power of 20 operation, then only the learning is done. According to OpenAI, since 2012, the amount of compute used in the largest AI training doubled in 3.4 months. By comparison, by Moore's law, the computation capability in CPU doubles in 2 years. In fact, since 2012, the amount of compute used in the largest AI training has grown by more than 300,000 times. Therefore, in one sense, our AI gets better not because of smarter or better algorithm, but because we have done much more computations compared to the past. But why do we need so many computations? There are mainly 2 factors. First, the models are much larger. Second, the data we use are much bigger. When it comes to building AI, for data, we do not just collect the data. To get a working AI model, we usually need to perform supervised learning. And in supervised learning, the AI model needs not just the data, it also needs to have the labels that correspond to the images, the text, the videos that we have collected. And creating these labels is nothing but easy. The picture at the bottom left shows a few gentlemen doing data labeling for their customer. This photo was taken at a Beijing data labeling office. These people are the invisible workers of the AI era, the data laborers who spend day and night annotating data for model training so that we can enjoy those machine learning empowered goods and services. In fact, data labeling has now by itself a big industry. Some self-driving companies are paying millions of dollars per month to data labeling companies. Data labeling is such a good business that a San Francisco-based data annotation startup called Scale AI has raised a blockbuster funding round of 100 million USD dollars. Data annotation has now become a billion-dollar business. But with so many computations and so many efforts spent to create state-of-the-art model, are they worth the price? Are those AI really learning in the way we learn? Are they making judgment in the way we do? Unfortunately, the answer is far from that. Just now, we have learned that self-driving companies have been paying millions per month for data labeling. They have also spent a lot of training. They have spent a lot in training a lot of AI models. But there are times the reality is not working in their favor. Here we have one interesting incident just recently posted on Reddit. There was a Tesla driver driving his Tesla on the road. In front of him, there was a truck carrying 3 mobile traffic lights. You can see that in the picture. Well, that was pretty normal. Nowadays, Tesla has an AI that can identify what is on the road and display on a screen. It looks something like the one at the bottom left in this slide. Now, with that truck in front of the Tesla, the AI system on Tesla, however, showed that the car was going through multiple traffic lights around him. The whole output looked as though a lot of traffic lights were flying towards the car. Let me play you the video to illustrate the point. You can see the traffic lights looks as though flying towards the car. Now, luckily, the driver was driving the car manually. Can you imagine? If the car is self-driving, how the car respond to those flying traffic lights? Will the display just show blue screen and the car stops immediately? So this is the current state of AI. It is not far-fetched to say that the progress of AI is mainly powered by improvement in hardware, especially the advance in GPU, the graphic processing unit, and TPU, the tensor processing unit. These hardwares enable intensive computation to complete in a relatively short time. For now, to get an AI trained, we need an enormous amount of data. We need not just data, but also the labels that correspond to the data. In one way, the AI we have is just a reflection of the data we collect. I always said the AI is as good as the data that you have. The AI cannot perform anything reliably beyond what your data has. We can comfortably say that the current AI does not learn in the way we humans learn. A child does not need to see 1,000 pictures of dogs and cats to identify them. For a child, a few photos will do, and the entire process uses much fewer energy compared to the power-hungry GPU. And furthermore, the current AI still has no common sense in the system. Now, given the issue stated in the above, one may wonder, can we have an AI that learns well with only a few examples and lesser amount of computation? Is it possible to have AI that learns like human? These are the questions some of the computer scientists are working on. And these are the questions few-shot learning is trying to answer. To understand if we can have an AI that learns well with only a few examples, and to understand if we can have AI that learns like human, we need to go back to understand the fundamental. We need to understand what machine learning is in general, what is few-shot learning, and what are the differences between the two. Here we have a formal definition on machine learning expressed solely in words. This formal definition was proposed by Michel in his 1997 book. Okay, I understand this statement is painfully unfriendly. Let me use layman terms to explain some of the keywords inside the sentence. The word experience is basically referring to a data set we use to train our model. For some classes of task T, the task can be a classification or regression. And AI is saying doing a classification when the AI tries to tell you what the thing is. Is this a picture of dog? Is this a picture of cat? Or is this a chest x-ray of a COVID-19 patient or a chest x-ray of a normal person? These are all classification. As for regression, in regression, the AI tries to predict a numeric value. For example, we may have an AI that predicts today's temperature, or an AI that predicts how many COVID-19 cases are we going to have today. These tasks are all considered as regression. For performance measure P, this thing helps us to understand how good our AI is. The most common metrics we use is, of course, accuracy, but beyond that, there are other measures for other purposes. Lastly, the phrase improve with E on T measured by P is basically saying that the performance of the model improves after the model trains with the dataset that we have. So by now, you should have a clearer understanding on what this definition is trying to say. We are going to encounter these few keywords again and again in later slides. We have seen the definition on machine learning. How about few-shot learning? Last year, a group of researchers from Hong Kong has published a review paper on few-shot learning. In that paper, they have provided a formal definition on few-shot learning. Let's take a look at the definition. According to them, few-shot learning is a type of machine learning problems where the experience E has limited number of samples with supervised information for the task T. Personally, I think this definition is a bit too broad and therefore not so useful in many circumstances. But according to the authors, they have to make the definition this broad in order to include many relevant research. Under few-shot learning, there are two special cases. The first one is called one-shot learning. Now, in machine learning, most of the time we are doing supervised learning. In other words, the dataset is come with a set of labels. These labels tell the AI what the inputs are during training. In one-shot learning, the amount of sample that comes with a label is pathetic. We have only one for each category, and the AI can only learn from one example for each category in this case. But this is not the saddest case. There are situations when the dataset has no label. In this situation, few-shot learning becomes zero-shot learning. Do take note, however, in zero-shot learning, since the dataset has no label, it needs to contain information of other modalities, such as words description, in order to provide the AI some level of supervised information so that the AI can learn. Personally, I think when your dataset has no label, either you try to get a label or probably the problem is not yet ready to be solved. Here, we have the comparison between machine learning and few-shot learning. You can see that in the case of machine learning, for experience E, we always need large amount of data and labels or annotation for the AI to work. But in the case of few-shot learning, we do not have that kind of luxury. For AI to work well, you can see that in the table, the experience is split into two parts. The first one is supervised information, and this refers to the limited data and label that we have. And the second part is prior knowledge. In case of image classification, the prior knowledge usually is the images and labels of other categories. We usually first expose the models to learn on that data set and then make our model to adapt on our small and limited data sets. For example, assume we want to have an AI that can identify images of sea lions and sharks. These two classes, sea lions and sharks. We have limited data and labels on that, but we have a lot of images and labels for dolphin, whale, penguin, and clownfish, let's say. So we get our AI first learns to differentiate between dolphin, whale, penguin, and clownfish. This is how we get the prior knowledge. After that, the AI will be exposed to our limited data and labels and try to discriminate between sea lions and sharks. In machine learning, this is usually how it works. We have the AI, the model that receives an input. In this case, the input is an email. The AI tries to identify if the email is a spam or is not a spam. In this scenario, only one input is required, and the AI will provide the correct output. This is pretty straightforward, but for this to happen, you need to have a lot of data and labels to train the model. But in few-shot learning, the working is not so simple and straightforward. Here we have a model that tries to predict the behavior of a molecule compound. This is a real-world problem. In general, we have plenty of molecules, the data, but many times, the behavior of the molecule, the label is not known to us. And thus, what we have at here is a few-shot learning problem. For each type of behavior, we have only limited number of samples. In figure, you can see that there are 6 inputs to the AI model. The first 5 inputs are molecules with known behavior. And the last one, styrene oxide, we do not know its behavior. In order to predict the behavior of styrene oxide, we need to provide 5 molecules with their corresponding supervised information to the AI. The AI will make a judgment and decide what behavior styrene oxide will be among the 5 given behaviors. So here is the output from the model. And this is just one of these, mainly the one key differences between machine learning and few-shot learning. In machine learning, we just provide the input to be classified or predicted. In few-shot learning, many times we need to provide what we call the support for the AI to make decisions. Why do we need to do that? This is simply because we do not have sufficient data and label for the AI to learn. By now, you should have a rough idea how few-shot learning works. Few-shot learning is tougher and complicated, but why do we want to do few-shot learning? There are 3 reasons. Sometimes supervised information are just hard to get or impossible to acquire due to privacy, safety, or ethics issues. We have mentioned one example just now, drug discovery. Another example is cold start item recommendation. This happens when a visitor visits a web platform for the first time, and at that time, the AI knows nothing about the visitor, and therefore it is hard to recommend item or product to the visitor. Reason number 2, the companies do not want to spend so much effort to collect so many supervised data. Sometimes the amount of data and labels required are just beyond their reach. Reason number 3, we want to build a machine that learns like human. We want to build an AI that makes decisions like human. This is a vision we always have since 1990s. So in the coming few slides, we are going to explore and understand why learning with small data is so hard, and there is a mathematical reason behind that. To understand the issue well, let's begin with a simple example. Assume we want to have an AI, a machine learning model that can make prediction about the amount of forest area being burned in a year. The prediction shall be based on solely one value, the forest dryness index. You can see the data in the bottom left in the screen. The value for the forest dryness index runs from -1 to 2 in our case, and the forest area burned is in the unit of 1,000 kilometers square. Since we want the model to make prediction based on forest dryness index, the input to the model is only the forest dryness index. For this, we shall use X to denote it. The output of the model is, of course, the area of the forest burned. For that, we shall use Y to denote it. So, X for forest dryness index, Y for the area of the forest burned. For this problem, we have 32 examples. You can see that in the chart. You can count them if you want. In the other words, we have 32 pairs of forest dryness index, and forest area burn. We shall use x underscore I and y underscore I to denote a pair of these values. Because we have 32 of them, the I runs from 1 to 32 to denote the 32 pairs. Computer scientists and mathematicians usually want things to be concise. So we can in fact denote what we have said just now into this simple mathematical expression. dtrain denotes the training data set we have. The curly bracket stands for a set. The AI model that we want in a more specialized terminology is called a hypothesis. We use H to denote hypothesis. The term hypothesis is a bit fancy, but it is just a function that can give us the output y based on the input x. In the figure at the bottom left, you can see a dotted line in red color. This line represents the correct model that we wish to get. This is the ideal correct model, and we call this model optimal hypothesis H hat. Now assume after some effort of investigation, we think the model or the hypothesis should be in the below form. Y equals to A times X squared plus B times X. We think, based on the data that we have, the model should look something like this. At this moment, we do not know the value of A and B, so the model of this form is our intellectual guess. How can we get the value of A and B? We know we have the data, so we are going to use the data we have to do some training. In other words, training a model is basically doing a search on A and B. That gives us a model that is close to the optimal hypothesis H hat. So now we know when we do training, we are looking for the magic numbers for A and B. These two items, A and B, that will give us a complete function, a complete hypothesis, are called parameters. We can consolidate these parameters and use one symbol to denote them. We shall use theta to denote parameters. With that, we can rewrite the hypothesis in this format. So we can see that there are two things in a hypothesis. The first one is the input, the x. The second one is the parameters, denoted as theta. Why do we want to express the hypothesis in this manner? The reason is this. Before the model can be deployed for use, we need to train the model. And the training of a model is a search on parameters, the theta. Now the A and B can be any real numbers. A can be 1.5, B can be 0.2, they can be any numbers. All these possible combinations of A and B form a hypothesis space. We use this curly H to denote the hypothesis space. We have mentioned that A and B can be any real number. Let's restrict ourselves that the A and B shall be only positive values. In this case, you can imagine this hypothesis space to be a 2D Cartesian coordinates, with A stands for the usual x-axis and B stands for the usual y-axis. We can take this rectangular gray area as the hypothesis space for our simple model. Inside this hypothesis space, we have a green dot. This represents a hypothesis with a randomly chosen A and B. On the other hand, we have a blue dot, which represents the optimal hypothesis H hat. The optimal hypothesis is what we are trying to get. With the data that we have, after some proper training, we get the best hypothesis with whatever we have. This hypothesis is denoted by a red dot and mathematically, it is expressed as H asterisk. Now, in reality, the best hypothesis H asterisk that we get after extensive training usually is not the optimal hypothesis H hat, although they can be pretty close to each other. You can get the feeling from the illustration. In fact, there is no guarantee that our training can even give us the best hypothesis H asterisk. To get just the best hypothesis H asterisk, we have to get things right on our algorithm, our model architecture, and more importantly, we need to make sure our data is sufficient and the quantity is large enough. In general, we assume they should have an optimal hypothesis, but we can never know what exactly that is. In other words, we believe the optimal hypothesis does exist. That's the reason we are working towards it. In training, we just try to get the best hypothesis using whatever we can, but this is not guaranteed. So here is a quick summary on what we have covered so far. We have seen most of the terms before, except the last two items at the bottom of the table. Let me briefly explain these two items. The curly L denotes a loss function. Loss function is basically a function that tells us how close is our prediction and the label that we have for a given input. We usually use y hat to denote the output of our model. We use y to denote the observed output. So the loss function tells us how correct or how wrong is the output from the model for that particular input. The last item in the table is called ground truth joint probability distributions. Now let's say we have a sample where x equals to 0.1 and y equals to 1. If we put x equals to 0.1 and y equals to 1 into this function p, the function will tell us how common we will see this combination of x and y in the problem we are working on. The output of the function is probability, which tells us how likely we are going to encounter this combination of x and y when x equals to 0.1 and y equals to 1. Now, in this simple example, the x is just the forest dryness index, and the theta consists of just A and B. However, for the same notation, the same concept and ideas also apply to those complicated problems. In case of image classification, the input will be an image. The output y can be sea lion or shark. It depends on the things you want the model to identify. As for the parameters, in this example, we have only 2 parameters. But in deep learning, we have millions or hundreds of millions of parameters. So the training on deep learning model is really a search on millions of parameters. And the corresponding hypothesis space is much, much, much larger and complicated. In the coming few slides, you're going to see a few complicated mathematical formulas. Do not worry if you do not understand the formula. You just need to know the ideas behind and their implications. We know that training is a search on parameters that give us the optimal hypothesis H hat. But how do we define optimal? What makes us to say a hypothesis is optimal? Mathematically, a hypothesis H is optimal if when we put this H into this equation, it gives us the lowest value compared with other hypotheses. This equation is called expected risk. Just a quick reminder, The curly L here stands for loss function. If you find the formula troubling, no worry, you just need to know one thing. You just need to know that in reality, we have no idea what is the PXY, the joint probability distribution. Because we do not know what is PXY, the equation on the expected risk is almost useless to us. The best we can do is find a way to approximate the equation of the expected risk. The approximation is called empirical risk, which basically does an average on all the losses we get in our training. From the above, we can see that training is a process that searches on the best parameters by minimizing this empirical risk. This shows how the search is guided. The search is guided by trying to minimize the empirical risk. With the exposure to the concept of expected risk and empirical risk, let us relook at the various types of hypotheses we have encountered in machine learning. So the optimal hypothesis H hat is a function that minimizes the expected risk. This is the ideal solution, and we do not know what that is. On the other hand, H asterisk is the best hypothesis we can get from the hypothesis space. Both hypothesis minimizes the expected risk, but there is a significant difference. H asterisk is one of the hypotheses in the hypothesis space. But for optimal hypothesis, this is not necessarily the case, and we do not know what this is. So H asterisk is the best we can possibly get. The last one, HM, this is the hypothesis we get by training. This is the hypothesis we get by minimizing empirical risk. You may wonder, why do we need to cook up these three items? Well, there are reasons doing these differentiations. In real life, what we get is always HM, the hypothesis that minimizes the empirical risk. And from here, you can see that we are at least 2 steps away to the optimal hypothesis. Therefore, one of the natural questions to ask, how can we get H asterisk? Assume we have ways to get H asterisk. Then the next thing we will start wondering is, can we make H asterisk very close to the optimal hypothesis, the H hat? We do not have the exact answer now, but we can get some guide from one equation. Here we are. Now I promise this is the last mathematical formula you will get to see in this talk. There is no other mathematical formula left. I will not go into the detail about this formula. You just need to know there are 2 types of errors where we train a model. The first one is called approximation error. It basically measures how close the H asterisk approximates the optimal hypothesis. Generally, we do not know the error, but various analyses have shown that models with large number of parameters tends to approximate optimal hypothesis better. From here, you can see why deep learning models in general work so well. They have huge number of parameters. The second error is called the estimation error. We can measure this. This error tells us how close the function HM approximates the H asterisk. This error is something we can work on. However, just now we know that models with large number of parameters tend to have smaller approximation error. But when it comes to estimation error, models with large number of parameters instead have larger estimation error. So, in order to reduce approximation error, we have to use large model. But when we use large model, the estimation error will be big. So what can we do? Fortunately, estimation error can be reduced by having larger number of samples in training. When training set is large and diverse, the empirical risk function approximates the expected risk function better, and therefore the HM will be closer to the H asterisk, and hence closer to the optimal hypothesis H hat. In other words, when the model is large, to reduce estimation error, we need to have large and diverse data set. Well, this is again why nowadays deep learning works. But this spells trouble for few-shot learning because our data set is small. So what the equation tells us about the situation when training data set is small? Here it is. When training data set is small, empirical risk does not approximate expected risk, and therefore the hypothesis HM overfits. Now we can see that what are the challenges few-shot learning is facing. First, to reduce the distance between the best hypothesis H asterisk and the optimal hypothesis H hat, we need to have large model. At the same time, for large model, we need to have large and diverse data set. If not, our model overfits. But we do not have the data and labels. We can see that in few-shot learning, we are heavily restricted by the limitation of data. To overcome these problems, there are three strategies available. First, we can search for some way to generate similar data. Since we do not have sufficient data, we can try to get some ways to generate some data that looks similar to our current data sets. Second, we need to look for large models that inherently have smaller estimation error. Third, we need to devise learning strategy that learns efficiently and minimally. And in the rest of the talk, we are going to take a look at the third strategy, the learning strategy for few-shot learning. Before we discuss the learning strategy for few-shot learning, let's revisit the definition on few-shot learning. We now know that few-shot learning is a type of machine learning problems where experience E has limited number of samples with supervised information for the task T. The authors have purposely made this definition this broad so that they can include many of the research published under this definition. However, under this definition, many of the research with the keyword few-shot learning actually overlap with other subfields in machine learning. In particular, the subfield of semi-supervised learning and imbalanced learning. In semi-supervised learning, the machine learning problem has small amount of labeled data with large amount of unlabeled data during training. In this kind of problem, the data is there, the data size is large, the issue is on label. The problem is asking for a solution that can label large amount of data based on the initial small amount of labeled data it has. Besides, there is a so-called weakly supervised learning with incomplete supervision, and some works with few-shot entitled are in fact a weakly supervised learning problem. These few-shot learnings are not true few-shot learnings. The true, pure blood version of few-shot learning usually is the one we say characterized by meta-learning. For today's talk, I will not discuss what is meta-learning, but this is how the definition of the few-shot learning will be updated. Under this definition, the computer program improves with experience on task T1, T2 until Tj. However, at the end, what we want is to use the computer program to perform task T asterisk. Do take note, task T asterisk is different from task T1, T2 until Tj. You can see the computer program is trained on a set of tasks, but is used to perform on a task different from the initial set of tasks. Furthermore, for classification, we often use the term n-way k-short classification. It means the data set we have has n classes. And for each class, we have k examples. So n for the number of classes, k for the number of examples. Usually k is small and n can be big. Let's take a look at the difference in learning between machine learning and few-shot learning. Assume we want to train a machine learning model that knows how to differentiate among images of cat, elephant, and deer. This is usually how we train the model. For machine learning, we need to collect lots of images of cat, elephant, and deer. Generally, I would suggest 1,000 images per class to get guaranteed results. So we are going to have 1,000 images for cat, 1,000 images for elephant, 1,000 images for deer. Now, for all the collected images, we do not use all of them for training. We usually need to do a split. For each class, we can set aside 600 images for training. And we can set aside another 200 images for validation. The model will be trained using the images from the training sets and validated using images from validation set to see how good the model performs after training. This forms what we call an epoch in the long journey of training a machine learning model. After that, we repeat the same process, train the model using images from the same training sets and validate a model using the same validation set. This completes the epoch 2. Do take note, in machine learning, the training sets never change. The same applies to validation sets. And we keep repeating the process. The epoch continues until we have a satisfactory model. Do take note that throughout all the epoch, the model is trained and validated on the same task. The task is to classify images of cat, elephant, and deer. There is no change in task. After training, we want to see how good the model really is. So we use the rest of the 200 images in each class to check the model performance. In this state, the model is again performing the same task, classifying images of cat, elephant, and deer. This is how the training in machine learning works. In few-shot learning, however, the training or the learning works differently. In few-shot learning, we do not use the keyword epoch. In fact, the training goes by task or episode. In this talk, I use the keyword task to make things easier to understand. What we are trying to do at here is to have a model that can differentiate 3 classes of images. And for each class, the model can only take a look at 2 images. In other words, we are looking at a 3-way 2-shot classification. 3 classes. For each class, we have 2 samples. In the first task, the model needs to learn to differentiate among images of butterfly, elephant, and deer. For each class, only 2 images are provided, and these 6 images form what we call the support set. To check the performance of the model, we have the query set, 1 image from each class, and this completes the training task 1. In general, the performance is unlikely to be good because the model is exposed only to 6 images in total. Well, You may think that since it is not good, let's repeat the same training again. This is a reasonable idea, but unfortunately, it won't work well. Instead, this is what happens next. In training task 2, the model is asked to differentiate among images of cat, dolphin, and koi. And similarly, for each class, only 2 images are provided. Training task 2 also has a query set, 1 image each from cat, dolphin, and koi to check the performance of the model. Now you can see that training task 2 is different from training task 1. In actual practice, we can have classes overlapping among tasks. For example, in training task 2, it is okay to get the model to differentiate among images of butterfly, dolphin, and koi. In this case, one of the classes in task 1 appears in task 2. That is fine. But we should not have had the same 3 classes in task 1 appearing exactly the same in any other later task. Why are we doing this? Because we want the algorithm to learn to classify image classes in general rather on a particular set. And the training continues. We will have task 4, task 5, task 6, etc. and none of the tasks is the same. We are doing this because the algorithm should learn the general way to differentiate images, not specific classes. When it comes to testing, few-shot learning also works differently. The testing in few-shot learning also goes by task. Furthermore, testing tasks are using images of classes not available in any of the training tasks. You can see that from the illustration. In training task 1, in testing task 1, the classes are owl, panda, and squirrel, and these 3 classes are not available in any of the training tasks. This is to ensure we can correctly measure the capability of the model in classifying image classes in general. Besides testing task 1, there are testing task 2, testing task 3, etc., which are not listed in this illustration, but expressed as ... at the right-hand side of the illustration. Now you can see that if we manage to get a model work well under these setups, the model is indeed going to behave more similarly to human, as it can differentiate images just by a few examples. In general, there are 2 main ways to achieve decent learning outcome for few-shot learning. The first one is called embedding comparators. The second one is called weight aggregators. In embedding comparators, the hypothesis, which is a function or just a model, generate embeddings on both the supports and query. After that, the embeddings are compared using some metric to determine a class. These embeddings usually are just vectors that describes the unique characteristics of an image. On the other hand, for weight aggregator, the algorithm searches for parameters that can produce hypotheses that adapts well to dataset with few examples and still generalize well. For today, to reduce the dose of mathematics in this talk and due to time constraint, I will only briefly introduce 3 methods in embedding comparators. The first one is called matching network. Here we are trying to do a 3-way 2-shot classification. There are 3 classes: butterfly, koi, and dolphin. Each class has 2 images. X hat is the query image we want to classify. In embedding comparators, the support set is always fed in together the query image, and all the support images go through the same hypothesis and generate the respective embeddings. For query image, it either go through the same hypothesis or it can go through a different hypothesis depending on the person who trained the model. In any case, another embedding is generated for the query image. Then these embeddings, in this example, 6 from support and 1 from query, are compared using attention mechanism with cosine similarity. The final output is some probability values. In our case, it should have 6 probability values, telling you how likely this query belongs to any of the support. The support that has the largest probability value is the class the matching network has determined for the query image. You may wonder how the hypothesis usually look like in matching network. If we are working on image classification, the hypothesis can be any convolutional neural network, but without the classifier part. Of course, we can use existing established or well-trained network like the VGGNet, the one we see here, or Inception or ResNet. For language-related tasks, the hypothesis can be simple form of word embedding. In matching network, we have seen how embeddings are generated, how embeddings are used and compared. For the coming 2 types of embeddings comparator, the working principle is pretty similar. We know that in few-shot learning, each class has few examples, but in reality, in the data we have collected, some classes may have fewer examples. When we have data set like that, the classes where we have more examples may dominate in training. This will create an issue for matching network. So the solution to this is called prototypical network. Instead of directly comparing embeddings of each support, we average the embeddings of same classes. The average embeddings are called prototype. It is as expressed as C in the illustration. In the illustration, we have C1, C2, and C3. These are the prototypes from each class, and the embeddings generated from the query image X hat is denoted as C hat. And C hat is directly compared with C1, C2, and C3 using Euclidean distance. The illustration at the bottom left shows the idea. Average X11, X12, we get C1. This is the prototype for butterfly. Average X21 and X22, we get C2. This is the prototype for elephant. Similarly, we can get the prototype C3 for dolphin. C hat is the embeddings from the query image X hat. So the prototype closest to the C hat is the class of the query image determined by the prototypical network. In this case, it is the dolphin. In matching and prototypical network, the embeddings are compared using cosine and Euclidean similarity. Computer scientists look at these 2 networks and wonder, can we use a more sophisticated method to compare embeddings? Going down the line of thought, they propose relation network. In relation network, the comparison is done using convolutional neural network. And the comparison is always performed between the embeddings from the query image and the embedding from a class. The output of the convolutional neural network, the output of the comparison is called relation score. So in this case, 3 rounds of comparisons are done between query image and the 3 classes. One comparison gives us 1 score. There are 3 classes, so there are 3 scores. The class with the largest score is the prediction or classification. Here is the comparison between 3 types of embeddings comparator. The general idea is similar. The difference mainly lies on the way they handle embeddings and how the comparisons are made. In conclusion, there are quite a few solutions proposed for few-shot learning, but no consensus on the best approach. We have seen 3 of them in this talk. Among the 3 on the mini ImageNet datasets, RelationNet performs better in 1 shot and prototypical network performs better in 5-shot learning. Few-shot learning is likely to become more important. We are trying to find ways to reduce the use of data to reduce the computation. More importantly, as a computer scientist, we really want to get an algorithm that can learn better and perform much more efficiently. Thank you so much for your attention.